In this video, we're going to take a look at applications of exponential functions. So we entitled this video Exponential Applications. So basically, what we're going to do is we're going to have an application or a model where we use an exponential equation, an exponential function, or a logarithmic equation or a logarithmic function inside of a word problem. Now, in an earlier video, we looked at the formula for percentage growth when that percentage is compounded m times per year. So the formula, if we start with an amount p compounded m times per year and have a growth rate of r for t years, is a equals p times 1 plus r over m raised to the mt power. In a similar way, we saw a formula if we have continually compounded interest and have a growth rate of r over t years. We would have a equals p times e raised to the r times t power. Now, this r, I should state, that's the growth rate. That's sort of a yearly growth rate in one sense, since we're dealing with t years. If the growth rate is in decades, then t could be in decades. If the growth rate were in thousands of years, then t could be made into thousands of years. That's in both of those cases, both the compounding m times per year or compounding continually. There's a couple of other formulas that are well-known exponential formulas as well. There's something called a doubling time formula. If I know that a certain amount doubles each time period of size d, so let's say that something doubles every 7 years, then I could put d as 7 and set t for years, and that would give me the amount is equal to starting amount times 2 raised to the t over d power. Hopefully that makes sense. Doubling means we multiply by 2. So if we double every 7 years, we put a d as 7, and then once t hits 7, that's a multiplication by 2. Once t hits 14, that's a multiplication by 2 squared, and so on and so forth. In a similar way, we have a half-time formula, which instead of doubling, we put 1/2 there. So instead of having a 2, we have a half. But d is the time it takes to half. Now, you can make this more general as well. If you know a tripling time, you could put 3 and then put d as the amount of time it takes to triple. If you had the time it takes to multiply by a factor of 5, you could put 5 in here and have that d be the time it takes to multiply by a factor of 5. But doubling time formulas and half-time formulas are of particular interest because people talk about doubling times and half times fairly often. Let's do an example. Let's say the average half-life of glyphosate in soil is 47 days. Create an equation for the amount of soil, the amount in the soil if you start with 450 milligrams in a cubic foot of soil using T for the number of days. And then how long until 50 milligrams is left in the soil. So we're given a half-life, an average half-life for glyphosate, and that is 47 days, according to this word problem. We'll create an equation. If we start with 450 in a cubic foot of soil, how much is going to be left after T days? And then we'll find out how long until 50 milligrams is left in the soil. Because we're talking about half-life, we're going to use that half-life formula or the half-time formula that we saw on the previous slide in this one in particular. So let's go ahead and set that up. The first thing I'm going to do is create that equation. And so it is A equals P times 1/2 T over D. Now, we know the half-life of glyphosate is 47 days. Since T is going to be a number of days, then I'll let D also be in number of days. So my D is going to be 47. It also says that we start with 450 milligrams in a cubic foot of soil. So this amount is going to be in a cubic foot of soil. This would be the equation that I want. Now we can turn that into a function by just thinking of A as my output and T as my input. That is, A is a function of T. But for right now, we'll just leave it as an equation. Typically, I don't rewrite it as a function notation unless specified. Then it says how long until 50 milligrams is left in the soil. Well, that means 50 is equal to 450 times 1/2 raised to the T over 47. We can solve this exponential equation the same way we solve any other exponential equation of base 1/2. I would start out by dividing both sides by 450. If I do that on the left-hand side, 50 divided by 450 becomes 1 over 9. And then I have this. 1/9 is equal to 1/2 times raised to the T over 47. And then I can either apply natural log to both sides, or I can take log base 1/2 of both sides. I think right now I'll just apply natural log to both sides. And if I do that, the left-hand side becomes natural log of 1/9. The right-hand side becomes natural log of 1/2 raised to the T over 47 power. Using the power rule of natural logs, I can set natural log of 1/9 equal to T over 47 times the natural log of 1/2. Now I can solve for T. I would divide both sides by 1/2, and then I'd multiply by 47. That would give me 47 times the natural log of 1/9 divided by the natural log of 1/2 is equal to t. Hopefully that makes sense. Divide both sides by natural log of 1/2 and then multiply by 47. When I do that, I end up with 148.99 approximately. Remember, this t was in days. So how long until 50 milligrams is left in the soil? About 149 days. So all that is our setup. We create using the halving time equation. We know the halving time is 47 days, so we put that here. And then we start with 450. And the question was, how long until 50 milligrams is left? So just solve this exponential equation. Again, I use natural log on both sides to solve. If you use log base 1/2, then it works out the exact same way in terms of the answer you get, but the process is slightly different. Let's do another example. Example 2 says, a certain bacteria doubles in size every hour and a half, so every 1.5 hours. Create an equation for the amount of bacteria in a dish if you start with 1,000 bacteria, using t as the number of hours after the start. Once we create that equation, then we'll answer the following questions. How many bacteria will be in the dish after 3 hours? How many will be in the dish after 5 hours? And how long until we get 1 million bacteria in the dish? If you want to try this on your own, push pause on the video and try this on your own. In a couple of seconds, I will show you how it's done. All right, this is telling me a time it takes to double. So I'm using my exponential formula with a doubling time here. So that's going to be A equals P times 2 to the T over D. T is amount in time. Time is going to be in hours in this case. And D is going to be the amount of time until we double. That's 1.5 hours. So I get T over 1.5 as my exponent. And then since we're starting with 1,000 bacteria, that's my P, my starting amount. Again, in money terms, we call that a principal. The first question said, after 3 hours, how much are we going to have? Well, after 3 hours, that's a time input. So I would replace the T with the number 3. Notice that 3 hours is double of 1.5. So what that is essentially 1,000, and then we're taking a doubling and then a doubling again. So 1 point in the first 1.5 hours, it doubles. in the second 1.5 hours, that would get us to 3 hours. It would double again. So there's 2 doubling time periods. And therefore, the amount is equal to 4,000. That's bacteria on this. Now, it's not as clean after 5 hours. If we're talking about after 5 hours, I do the exact same thing, but 5 does not divide by 1.5 really easily. Doesn't, not as a whole number anyways. So we can still do it. We're just going to get an uglier decimal in this case. So we start with 1,000, we'd multiply it times 2, raised to the 5 over 1.5 power. So the amount that we have is 10,079.37 bacteria. I should say approximately because that's a rounded number. Now I've rounded this to the second decimal place, so the 10th. Other people may want you to round this to the whole number because you can't have 0.37 of a bacteria. But there you go. This one was exact, this one was rounded. And again, I get this rounded number because I have kind of an ugly exponent there. 5 over 1.5 is 3 1/3. So not a super easy exponent to deal with. The last question says, how long until we have 1 million bacteria? All I have to do is set 1 million as my value of A. That's equal to 1,000 times 2 raised to the T over 1.5 power. The first thing that I would do is I'd take my 1 million and divide it by 1,000. If I do that, I get 1,000 on the left-hand side is equal to 2 raised to the T over 1.5 power. Let me put this on the next page just so we can see it easier. Now, in the last problem, I took a natural log of both sides. So I'll do it the other way on this problem. If you want to do it the exact same way we did on last problem, you can take a natural log of both sides, use the power rule. But on this problem, I'm going to take a log base 2 of both sides, since we have 2 as the base of my exponential part. So log base 2 of 1,000 is going to be equal to log base 2 of 2 raised to the T over 1.5 power. I'll put that 2 inside of parentheses just so it looks a little bit different. There you go. And then what we have is the inverse property of logs and exponentials. That is, the log base 2 of 2 raised to a power is just going to give me that power. So I have log base 2 of 1,000 is equal to T divided by 1.5. Multiplying both sides by 1.5, I'd get 1.5 times the log base 2 of 1,000 is equal to T. Now that's the exact value of how long it will take to hit a million bacteria. But if I want, I can get an approximation for that by typing this into my calculator directly, if my calculator has this property, or by doing a change of base, like natural log of 1,000 divided by natural log of 2, and then times 1.5. Either way, we can solve. Again, change of base rule, or plug it into your calculator. I end up with about 14.95. Now be careful about this, because in my original problem, t and 1.5 were both in hours. So t is number of hours, d is in number of hours. 1.5 hours, t is in number of hours. So when we say 14.95, that is in hours. So there you go. We see that we can solve how long it takes to get to a certain amount. And also, we can just plug in and see how much we have after certain number of hours. And as always, check for the rounding that you would want. Like I said, I rounded this to 2 decimal places. Some people may round this to the nearest whole number. I rounded this to 2 decimal places. Some people may round this into the nearest whole number of hours. Or some people might want you to write it down in hours and minutes and seconds and then convert it that way. In any case, just adjust this if needed as far as rounding goes. Let's do another example. This says a city had a population of 45,600 people in 1995. Since then, the population has approximately decayed continually at a rate of 0.8%. Create an equation for the population of the city using t for the number of years since 1995. After we do that, what we'll do is we'll ask, if this rate continues, what will the population be in 2035? And then we'll say, in what year did the population reach 40,000, or will the population reach 40,000? And then lastly, how long until the population gets halved? So gets cut in half. If you want to push pause on the video and try this problem on your own, feel free to do that. In a couple of seconds, I will show you how it's done. All right, now the first thing we're going to notice is that it says the population has decayed continually. That word continually is telling us that we're using A equals PE raised to the RT power. And in this case, the initial population is the population in 1995, which is 45,600. The E is obviously the number E. And then it says we are decaying at a rate of 0.8%. Now be very careful about this. Decaying is going to give me a negative. 0.8% is 0.008. Don't write 0.8, that would be 80%. 0.008 is 0.8%. And then T is the number of years since that initial time of 1995. Now, if this rate continues, what will the population be in 2035? To find my T, I'm going to take 2035 and subtract 1995. That's a T of 40. So it took 40 years from 1995 to 2035. The population is going to be the the amount. So we take 45,600 times E raised to the negative 0.008 times 40. T is in number of years since 1995. This is the exact amount. Obviously, we're going to put this into our calculator and get an approximate amount. So just type that in, 45,600 multiplied times E to the negative 0.008 times 40 becomes 33,112.40 if I round to 2 decimal places. 33,112 if I round to the nearest whole number. So that's the amount of people or the population that we project to have in 2035. In what year did the population reach 40,000 people? Well, that is an A of 40,000. And we're setting that equal to 45,600 times E raised to the negative 0.008 T. And then all we have to do is solve for T there. We know how to do this. Divide both sides by 45,600. If I take 40,000 and divide by 45,600, I get an ugly decimal, which as a reduced fraction is 50 over 57. That's equal to E to the negative 0.008 times T. Now I would apply natural log to both sides. If I apply natural log to both sides, I get natural log of that fraction, 50 over 57. By the way, you don't have to reduce your fractions. If you wanted to keep this as 40,000 divided by 45,600, you could keep it that way too, if you'd like. But that's equal to natural log of E to that power. Inverse property of natural log and E to a power makes that right-hand side become negative 0.008 times T. And then I can solve this by simply dividing both sides by a negative 0.008. So I'd take natural log of 50 over 57, or like I said, if you want to keep it as 40,000 over 45,600, that's fine too, and divide it by negative 0.008. That gives you your exact value for T. Obviously, we could probably come up with a rounded version in this case. So I type that into my calculator and get a T of about 16.38. Now that is years after 1995. So that means we're about in the middle of 2011. So sometime in 2011. and before 2012. It's like 2011.38 if we're precise. I'll write it that way. Sometime around 2011.38. So I don't know, a little bit into 2011. But the key there is I just set 40,000 equal to the amount and then solve for t using the techniques that we already know. Application, applying natural log to both sides. Now, the next one says, how long until the population gets cut in half? Well, we start out with 45,600. If I were to cut that in half, that would mean I would half the 45,600 and get 22,800. So how long until the population gets cut in half? That would require me to solve this problem. Now, here's the nice thing. If you divide both sides by 45,600, you end up with a half on the left-hand side. And on the right-hand side, it's e to the power negative 0.008 times t. Notice that would have worked no matter what we started with. If I started with 45,600 and half that, then I would have ended up here. If I would have started with 2 people and then went down to 1, it would have been the exact same at this stage. So regardless of how many people we start with, if we have the fact that we are declining at a rate of 0.8%, the amount of time until the population gets cut in half is always solved using this formula. Now we can apply natural log to both sides. Natural log of 1/2 is the left-hand side. The right-hand side is natural log of e raised to the negative 0.008 times t power. Not sure why that didn't. And then the right-hand side becomes just negative 0.008 t. Dividing both sides by negative 0.008 gives me, well, I'm just going to give the approximate value, 86.64, approximately. So it would take 86.64, that is years after 1995, until the population gets cut in half. And that's in a year about 2081. That's after 2081, but before it hits 2082. So that's how we can solve things like how long until the population gets cut in half. All of that came from our original formula, or our original equation, our original function here. And then we could plug in values for t, solve for a. And now we can plug in values for a and solve for t. Let's do another example. This says iodine 125 decays continually at a rate of 1.15% per day. So the rate is given to us in a daily rate, but we're decaying continually. Then it asks, what is the half-life of iodine 125? Second, if a doctor injected 60 milligrams into your body for a scan, how much would be left 50 days after the injection? So be careful on this one. This percentage is per day. So when we use our formula, we're going to use T as the number of days. And it's going to be decaying continually. So we'll be using A equals P times e to the RT. Let's set that up. So decaying continually at a rate of 1.15% per day. Again, we're going to say T is going to be in days because we're talking about decay rates in terms of days. So we're going to set it up as A equals P times e to the negative 0.0115 times T. That's 1.15% translated into a decimal. And then since it's decay, it becomes a negative rate. Now, it doesn't tell me how much I start with. 125 is just the isotope of iodine that we're talking about. It is not the amount. So it doesn't tell me the amount that I start with, so I'm going to leave that as just P. If it says, what is the half-life of iodine 125, you may say, well, it doesn't tell me what the P and the A need to be. But from the previous question, we know that if I make A half of whatever I make P, then I can get the right answer. So let A be 1 and P be 2, or let P be 1 and A be a half. Maybe it's a half of a pound or a half of a milligram or something like that. So whatever we start with, just let A be half of that. Now we can apply the natural log to both sides. If I apply the natural log to the right-hand side, I end up getting just the exponent. Sometimes people will skip this step that I'm currently writing and write the next step only. They'll say, well, then take the natural log of 1/2 and set that equal to a negative 0.0115 times T. Notice solving this equation was very much like solving the equation we did in our last example. So go ahead and approximate this. That's natural log of 1/2 divided by negative 0.0115. And that T value is approximately 60.27. That's in days. Remember, T was in days because our percentage rate of decline was also in days. So 60.27 days. Now, if a doctor injected 60 milligrams into your body for a scan, how much would be left 50 days after? I'm actually going to do this in two different ways. I'm going to start with this equation. This is how I would do it. I would say if the doctor injected 60 milligrams, how much would be left 50 days after? I'd plug in a T of 50. So P of 60 and T of 50. We take 60 multiplied times E raised to the negative 0.0115 times 50. If you did that, you would get the amount is approximately equal to 33.76. Again, that would be in milligrams. Now, another way you can do that is now that you know that the half-life is about 60.27, you can actually, this is not the way I recommend because that 60.27 is a rounded version, but you could take 60, and since you know that the half-life is 60.27, the equation for the halving time would look something like this, although again, this 60.27 is a rounded number. Then if you plugged in 50 for that t, you would get roughly the same thing. I hit the wrong button, sorry. You'd get right about 33.76 again. And you'd be a little bit more accurate. You'd be exactly the same if this 60.27 got replaced with its exact value from up here. But you could have done it this way as well. Again, I don't recommend this way now that you know the half-life because this is a rounded number. This 60.27 is a rounded number. But you could do it either way, especially if you get the exact value. Notice that this means this equation, if I just replace the 50 with a t, and this equation, replacing the 50 with a t, are actually the same equations, just written differently. Like 1/2 raised to the 1 over 60.27 power is the same thing as e raised to the negative 0.0115 power. Interestingly enough. Again, I would recommend this way since these are not rounded numbers. And I would avoid this way because that 60.27 is a rounded number. But I did want to point out that these are the same things, just written differently. Let's do another problem. In example 5, it says, a biologist records an estimated 450 bluegill in a pond 6 years after its construction. 5 years after that time, so 11 years after construction, he measures an estimated 1,400 bluegill in the pond. Create an equation for the amount of bluegill in the pond T years after construction, assuming continuous exponential growth. And then find how many bluegill were in the pond initially. And if this pattern persists, how many years will it take for the pond to have its carrying capacity of 2,500 bluegill? In other words, how many years until it hits 2,500 bluegill? If you want to try this one on your own, push pause on the video. I'll show you how this is done in just a little bit. All right, so we know that since it's continuous exponential growth, the equation is going to be something of the form A equals P times e to the RT. Now, the T here is going to stand for years after construction. So we know a couple of things. We know that 450 bluegill are in the pond 6 years after construction. So we have 450 are in there 6 years after construction. That means 450 is equal to P times E to the R times 6. And then 1,400 bluegill, that's fish. Hopefully everybody knows that a bluegill is a type of a fish. 1,400 are in 11 years after construction. So I know these two pieces of information, and I'm going to use those two pieces of information to figure out what the R and the P is in this general equation. Now, the way we do this is we actually divide both sides. It's going to be a little bit easier if I take the second equation and then divide by the first. Since 450 is equal to P times e to the R times 6, I can take 1,400 and divide it by 450 on the left-hand side and set that equal to P times E. I'm going to write that as 11R instead of R times 11, divided by P times E to the 6R that way. When I take 1,400 and divide by 450, I get a reduced fraction of 28 over 9. So I'll write 28 over 9 on the left-hand side of that equation. On the right-hand side, the p's will cancel, and then e to the 11r divided by e to the 6r is actually e raised to the 5r. We subtract the exponents. So p's cancel, and then I subtract exponents since we have the same base. Now I can find r fairly easily by taking natural log of both sides. Natural log of 28 over 9 is equal to 5 times r, and then divide by 5. So natural log of 28 over 9, all divided by 5, is equal to r. Now that's the exact value for r. Obviously, we can type that into our calculator and see that r is about 0.227. I won't write the approximate value in the equation, but I will write the approximate value here, 0.2270. The interpretation of that is that the number of bluegill are increasing by about 22 or 23% per year. Now that I know that, I can plug it in to either this equation or to this equation to get my answer for P. I'll use this first equation. 450 is equal to P times E to the E to the 6R, or R times 6. And now we know that R is the natural log of 28 over 9, all divided by 5. That's a really ugly exponent, but this is all just a real number. So I can take 450 and divide by that real number. If it makes you feel better, then obviously you can rewrite this as a decimal and say e to 6 times whatever that 0.2270 decimal. I am going to type this into my calculator as 450 divided by e to that power, 6 times natural log of 28 over 9 divided by 5. I ended up getting a p-value which is approximately 115.27. That's how many bluegill are in the pond initially. I'll use the rounded number there. By the way, that is my first question. How many bluegill were in the pond initially? We would say approximately 115.27. Again, these are estimated numbers. And by the way, the actual equation would be A is equal to 115.27, again, roughly, times E to the R. We just found out that R was 0.2270. More specifically, this ugly value, which is about 0.2270, times T. So that's my equation with a rounded P and rounded R. And we'll just use rounded values from here on out. If this pattern persists, how long will it take to reach 2,500 bluegill? That's saying the amount we have at the end is 2,500. So we're just solving this equation for T. And we do that just like we always do. Take 2,500, divide by 115.27, set that equal to E to that power. Take a natural log of both sides. I'm going to not write every step. If I take natural log of the left, I get natural log of that fraction. Natural log of the right cancels out with the e to the power and just gives me the power itself. And then I can take natural log of 2,500 divided by 115.27. I'll use the rounded value when I type it in this time, and divide that by 0.2270. So divide the left-hand side by 0.2270. We get a T of about 13.55. So it would take about 13.55 years after the pond was built until it hits its carrying capacity of 2,500 bluegill. So there we go. Now the key thing there was this technique that since we have one piece of information and another piece of information, that's like 2 points on our graph, we can divide both sides and come up with the R value. Once I have the R value, again, some people would just use the decimal version of the R value. Once I have that, then I can come up with the initial amount of bluegill, and that gives me the general equation. Again, some people may want you to round the initial amount to a whole number. Sometimes the R value, they may want you to round to 2 decimal places, or maybe they'll want you to round to 4, but that's all the same technique aside from just rounding differences. So there we go. Let's do another example, but this time let's not compound continually. This says you invest money into a stock at 6% interest compounding monthly. How long until your investment doubles? How long until your investment triples? And then if I invest $400 today, how long until we have $2,100? Go ahead and push pause on the video if you want to try this. Obviously, we're compounding monthly, so we have to use the appropriate formula. In a couple of seconds, I will show you how it's done. All right, so since we are compounding monthly, we're going to be using the formula A equals P times the quantity 1 plus R over M to the MT power. Oops. And in this case, since we're compounding monthly, my M is going to be 12. Since we're at 6% interest, my R is going to be 0.06. Now, I don't know what my P is. It doesn't tell me what the initial investment is at the beginning here. So we get 0.006 divided by 12 as the R over M. And then my exponent is going to be 12 times T. Now, if we're asking how long until the investment doubles, all we have to do is put 2 in for the A and 1 in for the P. Because that's like taking $1 and doubling it to 2. And then I can solve this. Now, just like always, we can solve this one of 2 ways. I think I'll solve this one way and then the tripling one another way. So I'll apply natural log to both sides here. Take natural log of 2 is equal to natural log of 1 plus 0.06 over 12, all raised to the 12t. Notice all of that is on the inside of the argument. Using the power rule of logarithms, that means natural log of 2 is equal to 12 times t times the natural log of 1 plus 0.06 over 12. And in order to solve for t is the thing we need because we need to figure out how long it takes. So we need to solve for t. I would start out by dividing both sides by that natural log of 1 plus 0.06 over 12. That would give us natural log of 2 divided by natural log of 1 plus 0.06 over 12. And that would be equal to 12t. And then I would divide everything by a 12. Now, in order to save typing, I'm just going to divide everything by a 12 right now. I'll put an extra 12 in the denominator there. So this is my exact value for how long it takes to double. The way I type that in on my calculator is I take natural log of 2 divided by natural log of 1 plus 0.06 over 12, and then hit enter, and then I divide another time by 12. And we get that the t value is approximately 11.58. In other words, it takes about 11.58 years in order for the investment to double. If we're doing this for how long it takes the investment to triple, well, that's the exact same argument, except the amount at the end is going to be triple the starting amount. And so I get 3 equals 1 times 1 plus 0.06 over 12 raised to the 12t. And I don't even have to write the 1. Now in the last problem, we did a very similar problem, except this was a 2 instead of a 3. We applied natural log to both sides. We could do that here as well. In fact, we get the same thing, except for all we have to do is replace this 2 with a 3. But I want to show the other way we could have done this too. We could have taken log, whose base is 1 plus 0.06 over 12 on both sides. Maybe that's an ugly look, so maybe I'll try to rewrite that a little bit with parentheses. So log of that ugly base of 3 is equal to log of that ugly base of my right-hand side. My right-hand side is 1 plus 0.06 over 12 raised to the 12t. Put that all inside there. And then this is what happens. If we use this ugly base, this 1.0612 log will cancel out with this base of my exponential. And what I would end up with on the right-hand side is simply 12t. Now the left-hand side is this. Log base 1 plus 0.06 over 12 of 3 is equal to 12t. And then I would just divide by 12. So I'd take that, divide that whole thing by 12, and that gives me a t. If I have the ability on my calculator to calculate this, then we can do that. Otherwise, I can use a change of base formula. And do it that way. So natural log of 3 divided by natural log of 1 plus 0.06 over 12, hit enter, and then divide that by 12. You get about 18.36. So it takes about 11.58 years to double, and takes about 18.36 years to triple. This last one is probably the just as straightforward. It's asking us how long until a $400 investment at 6% interest compounded monthly, how long until that becomes 2,100? The first thing I would do is divide both sides by 400. That would give me 5.25 is equal to 1 plus 0.06 over 12 raised to the 12t. And then again, you could take either natural log or you could take log base 1 plus 0.06 over 12. I prefer to take natural log, so I'll do natural log of both sides. Natural log of 5.25 is equal to the natural log of that right-hand side. Again, that right-hand side is this. And I take the 12t in the exponent and bring it out front. Whoops. Typing miscue there. So I get natural log of 5.25 is equal to 12t times natural log of 1 plus 0.06 over 12. Just like we've done before, we divide by that natural log. Natural log of 5.25 divided by natural log of 1 plus 0.06 divided by 12. That's set equal to 12t, and then I would divide both sides by 12. Again, what I typically do when I'm writing it down is I just write the 12 in the denominator, but when I type it into my calculator, I type in natural log of 5.25 divided by natural log of 1 plus 0.06 over 12, and then hit enter and then divide it by 12. I get a t value of approximately 27.71 years. So at 6% interest, it's taking about 27, 28 years to go from 400 to 2,100. Again, you can solve these types of equations by applying natural log to both sides and then using the power rule, or you could apply the log of this ugly base to both sides and use the inverse rule of logarithms and exponentials to just get the exponent there. So there you go. That's how to do problems like these. Let's do one last example. Let's find something called the doubling time. So assume we invest in a company and this company is growing at a rate which is compounding continually. What is the doubling time if the growth rate is at 5%? And then what is the doubling time if the growth rate is at 10%? Go ahead and push pause on the video if you'd like to try this on your own. In a couple of seconds, I will show you how this is done. All right, if the growth is compounding continually, then we're in the A equals P times e to the RT scenario. Doubling time, we've dealt with how long it takes to double before. Think of P being 1 and A being 2. So if we're calculating the doubling time, if the rate is 5%, we start with this equation, 2 equals e to the 0.05 times t power. Applying natural log to both sides would give me natural log of 2 is equal to natural log of e to the 0.05 times t power. We know what happens on the right. On the right, we just get the exponent because of the inverse property of logs and exponentials. So we would end up with natural log of 2 is equal to 0.05 times t. So we get the natural log of 2, and then we divide that by 0.05. Make sure you calculate the natural log of 2 before you divide by 0.05. That gives the value of t. So that as an approximate value gives me 13.86 years. So it would take about 13.86 years in order to double. What if the growth rate were 10%? Well, if the growth rate were 10%, we'd start out in the same type of scenario, but we'd have a different exponent of 0.10 times t. Taking natural log of both sides would give me, well, if I take the natural log of the right, I just get back the exponent. And notice that in order to find t, we're taking natural log of 2 and simply dividing it by 0.10. That gives me an approximate value of 6.93 years. By the way, notice that 6.93, if you doubled that, you'd get 13.86. That's not a coincidence because we see how we ended up with t. We just got natural log of 2 divided by the percentage rate as a decimal. In fact, if we were to say, what's the doubling time if the growth rate is, let's make up a percentage, let's say is 12%. We know that we'd have to solve it in the exact same way, and that my value of t would be solved by taking natural log of 2 divided by 0.12 for the exact same reason I did up here. I'd take 2 equals e to the 0.12 times t, and then natural log of both sides, and then divide by the 0.12 in the same way I did here. The same way I did above, excuse me. And in this case, t would be about 5.78. Notice that the doubling time is always just the natural log of 2 divided by the percent in decimal form. Now, interesting enough, there's something called a rule of 70 in finance. And it actually is referring to the doubling time. It says basically the doubling time is approximately always equal to 70 divided by the percentage rate of growth. So how does that work with our example? Well, what if we would have done the rule of 70 with, let's do it with 5% growth and 10% growth. If we have 5% growth, then the rule of 70 would say that the doubling time, we'll call it D for this, is approximately 70 divided by my growth in a percent mode. So 70 divided by 5, which obviously is 14. Remember what I got from my number was 13.86. If we had 10% growth, the rule of 70 for my doubling time says my doubling time is approximately 70 over 10, which would be 7. Remember what I got is 6.93. So that's a pretty decent estimate of what we were doing. And with 12%, we could do the doubling time with a 12% growth as well. Let's just type that in. Doubling time would be approximately 70 divided by 12. 70 divided by 12 is about 5.83. And we ended up with 5.78. So again, pretty close to what we came up with. Now, again, rule of 70 is basically a shorthand for what's going on up here. Notice that in each of these cases, I'm taking the natural log of 2 and dividing it by my percentage as a decimal. The reason that the rule of 70 works is that the natural log of 2, let's take it over 0.12. Well, the natural log of 2 is approximately 0.69. It's 0.6931471,806, and then it keeps going and going and going. And so that's like 69 over 12, or 69.3 over 12 if I move the decimal place over. So it's like 69.31 divided by 12 if I move the decimal place over. So that's about 70 over 12. That's where the rule of 70 comes from. The rule of 70 would probably be a little bit more accurate if we called it the rule of 69, but people don't usually use that. They typically call it the rule of 70. Anyways, I'm not going to ask you questions about the rule of 70. I did want to just show you why that works, why they can use the rule of 70 in finance. It's basically a shorthand for trying to solve this when people don't actually know how to solve this. And so it's an approximation for solving that. Hopefully that all makes sense. So in this video, we've seen lots of different exponential formulas and solved things with these exponential formulas. We had half-time formula. We had the doubling time formula. We had percentage with continual growth formula and the percentage with growth compounding m times per year formula. All of those were different exponential equations that we could utilize when solving problems. So that's the end of this video on exponential equations. Hopefully you saw how we could use the properties of logarithms to solve lots of these exponential applications.